Hello and welcome to today's video. Today's video is for Advanced Geometry, Chapter 7, Section 2, Similar Polygons. So just like when we did congruence, we had one section that talked about congruence for any polygon, and then we started working with triangles, and they had their own theorems and postulates for just triangles. We're going to do something similar for similarity, and that is we're going to have one section that deals with similarity for any polygon, and then we're going to talk about similarity in specifically in triangles, and there'll be theorems and postulates that'll make it a little more convenient to do triangles. Okay. So two polygons are similar by definition if all the corresponding angles are congruent and all the corresponding sides are in the same proportion, or they are proportional. Okay. The similarity ratio is the ratio of the lengths of the similar sides, or the corresponding sides of the similar objects. And from your earlier math, I know you did a similarity unit where you talked about, the similarity ratios and copy ratios and things like that. So it's important to remember that similarity ratio is a one-dimensional comparison of objects, and we will look at ratio of areas and volumes eventually. Okay. So completing this statement, if these two things are similar, notice this symbol for similarity. It's kind of like the congruent symbol without the equal. So if we draw a tilde, this means similar. So if I have two polygons that are similar, then angle E would be congruent to angle A. Easiest thing to do is to look, they have to be in corresponding order, so E matches up with A, so it's got to be measure of angle A. Now here's the ratio part. So the ratio of the corresponding sides have to be the same. So AB over EF, that works out, equals AD, well that would be the first and the last letters, over EH. So I can do that without even looking at the picture. You just make sure that you do the points in the right order. So to determine whether polygons are similar, by definition of similarity, I need to make sure that we have three sets of congruent angles. So if you look at this diagram, I do. Angle A and angle F are congruent, and then I also have B and E, and then I also have C and D. And then I also have to make sure all three sides are in the same proportion. So what I can do is I can start with 15, and then I can find its similar side, so that would match up to 20. And I want to know, is that equal to, how about I'll grab 12 next, and 12 matches up with 16. And then one more, 18 and 24. So this one you can divide by the 5 and it reduces to 3/4. This one you can divide by the 3. Sorry. This one you can divide by the 4 and you get 3/4. And this one you can divide by the 6 and you get 3/4. And so these are all in the same proportion. Okay. If these two figures are similar, find the value of x. So they tell me how they're similar, and it looks like they're similar in the exact same way they're oriented. So what I can do is I can find one set of sides that I know. So I know the 5 and the 6. And I can use those to set up a ratio. And then I can use one side that I know and one side that I'm trying to find to write another ratio. So 5 goes first, so 2 has to go first on the top, 2 over x, and now I can cross multiply. So 5x equals 12, divide by the 5, and x equals 12x. So this problem I do want to do in class, so remind me if I forget. It deals with a magnification system. So what it's asking is the video screen picture is 16 inches by 12 inches tall. What's the largest complete video image possible for a block of text that is 4 inches or 6 inches by 4 inches? So what they're saying is how big could I make this appear on the screen so that it fully appears on the screen? There might be a little extra left over where, you know, there's nothing written, but I can't have it go off the screen. So what we want to look at is to see if are these similar, and if they're not similar, then we have to make it so that it fits on the screen. And we'll do that one in class. We did a section on the golden ratio, but this is the book, and the book doesn't do much with this at all. So most of what we're going to do in the golden ratio is what we learned in class. So a golden rectangle is a rectangle that can be divided into a square and a rectangle that is similar to the original. If you start with any square, you can make a golden rectangle by putting a rectangle on the end such that the ratio, the triangle, or sorry, the rectangle you added is similar to the whole one that you created. Okay. In any golden rectangle, there's a golden ratio, and it's the ratio of the length to width, which is about 1.618. You are allowed to use that in like word problems and things like that, but we also want you to know the exact value, which is 1 plus root 5 over 2. So an artist plans to paint a picture. He wants the canvas to be a golden rectangle with its longer horizontal side, 30 centimeters wide, and how high should the canvas be? So this is another one I want to do in class. So what we're going to do is set up similar rectangles. Now, when you look at the book, they use the 1.618. We're not. We're going to actually use the actual ratio and find what exactly that side should be. So it'll be a little more fun. But I will also do that one in class. And I believe that is it for today's notes. Thank you for watching. Have a great day. Take care.